Yes, this lecture is a continuation of lecture one, and if you haven't seen lecture one, you definitely got to go back and pick it up. But this is not really it's not really a requirement to listen through lecture two. Yeah, I mean it's at some point that we'll be probably starting probably lecture four, which is right after, is the way I've got it in my head is that's going to build on lecture three, two and one. But yeah, this one, you don't have to have seen lecture one in order to go through this one. So another question. Okay, so yeah, that's it. So let's answer that. All right, so let's without further ado, let's get started. All right, so what this is the agenda for tonight. First thing I'm going to do is go through the logistics again. I want to just emphasize some of the things in there, and then we'll really get into it, get deep into it, which that's where we will continue from last time. But I'm starting with the beginning of this section, which is what is data science. I'm going to talk about the different types of machine learning, and then it's part of the data science. What is data science is different aspects of machine learning, how in a theoretical sense we're going to apply them. Then we're going to go into some demonstrations, showing you some of the applications in machine learning, starting with way back early stuff, and then looking at what's current applications in machine learning. And when I say current, beginning in the past 10 years. And then future is, where are we going with this? We'll talk about that some. Then, once we get through that, we're going to get into my favorite subject, which is neural networks. And I'm going to develop neural networks from scratch. We're not going to get into the math or the computing part of it just yet. All I'm going to do tonight is high level. Where did they come from? Where did we get this idea? What where is it going? How did it get from A to B? And then we're going to talk about the homework. And homework for this week coming up is the same as last week, plus a couple of things. So, all right. So just a little bit about me. I'm going to throw this slide up every time. Just so you have my LinkedIn, my email address, website, phone number, and feel free to reach out to me. I love new contacts. I'd love to get to know some people here better, especially if you're in the Bay Area. Also down in LA, we get down there a few times a year. Or anywhere in the country. If you want more information, if you just feel that it would be better to talk, I'm definitely open for discussions. I would be very, very excited to speak with some of you, one-on-one. So please, that's my phone number. Okay, yeah, and if you want to know more about me, if you haven't watched it already, I talked a lot about it in lecture one, but you can go through the Kate Strachny's. She interviewed me I talk about my background, how I got into machine learning, um, and how I got to where I am now and where I'm going. So yeah, you can check that out. And of course, Kyle and Randy and Chris, I need to add Chris's name on here. This is, just an exciting opportunity. I was, I was planning on doing this just for my company and opening up to, LinkedIn, but, since I'm in data science dream job, um, Kyle was like, I think it'd be cool to open it up to the DSDJ folks, and I did that, and it's awesome, wonderful. Um, let's see, definitely talk to them, talk to Kyle if you're not in it, and you want to explore further getting into data science, because they have a great program that really pushes you. Uh, just gets you there, get you off the fence. And then I talked a little bit last week about my underwater hockey. I don't know if any of you looked it up, but played last night. It was a blast. It is every Wednesday night and whenever else I get to do it. So logistics, just real quick, I'm going to run down this. I'm not requiring a whole lot of math here. Let's, just basic math. And I require for you to have a laptop, because you are going to be following along with me, and you will have projects and homework that are in Python at a minimum. Minimal programming experience, just, having done it at least once, that would be good. So you kind of know, but we've got a nice community that can help. Like when we play underwater hockey, some of the players that come out for the first time have never snorkeled before, aren't great swimmers, but they play, and we teach them. We help them out. We give them equipment, all this stuff. So same here. And toward that end, I've created a Slack channel or Slack workspace for the deeper side of learning, which is my website, and for this, mainly for this class. That's kind of what my website is built around at this point. So definitely get on there. It's part of the homework for this week. If you aren't already on there, got a whole bunch of people on there already, so I'm very, very happy. And post stuff, go to welcome and introduce yourself, welcome others, get to know people. We'll be doing a lot in that over time. That's how we will communicate during the week. Unless, we need to do more like email, phone call, whatever. And then there will be, they've got the homework assignments, which initially is getting going with programming, and there will be a final project at the end. So we will talk about that much more as we go along. All right, so this is quickly on the calendar. I'm getting ready to expand out. I know I've got this only going for 3 weeks, but I'm going to expand it out all the way to, for all the days that it's going to be. I'm going to do that this weekend. And everybody will just kind of be grandfathered in. For non-DSDJ or the Cost Plus, my coworkers, there will be a fee for the lectures. So we'll have to discuss that. I'm setting it at 20 per lecture, or for all of them 150, but we can talk if that's going to be an issue. The lectures are 1 to 1.5 hours. Last week it was 1.5, and could have gone to 2 hours, 2.5 easy with what I had prepared. So we'll have to monitor that. Getting used to this time frame, this 1.5 hours. There's what I want to get through, and then there's what we have time for. And this is all recorded. Actually, I need to change that. It's not under recordings under lectures, which I send out an email to everybody with that kind of information. So, okay, and just real quick, again, this is I'm kind of going through all this for some people that have joined late and that haven't seen the first lecture. So this is what we're going to be, at high level, what we're going to go through overall. Purpose, I'm still on the purpose of this, which is all about data science and about high level machine learning. Then we'll get into basics of neural networks, which that will be tonight. Then we will talk about what mathematics you need for machine learning. And there isn't a whole lot. Not to apply machine learning in a very effective way, you don't need a lot. There's definitely some, and we will go through that, some statistics or statistics, whichever you want to call it. And then linear algebra, some of that, tiny bit of derivatives, area under the curve. So it's an integral, but that's, I wouldn't worry about it if your math, if you don't remember all the calculus, will be just fine. Computing, we'll also do the computing for analytics and computing for machine learning, and that's when we will step back from neural networks, in the deep part of machine learning, the advanced, and then we'll go back and look at the statistical methods for doing machine learning, which are much older than the applied neural networks, and but extremely useful and mostly are what are used today for many applications, for most non-visual, I would say, applications, and maybe the NLP, natural language processing. There's just statistical methods are much easier to grasp. Many people have a much easier time with that. They've been around much longer as far as applications go. But I always get excited about applying neural networks. But we will go through to give you a well-grounded view of the way things are today. Okay, then we are going to jump deeper into machine learning. Actually, yeah, that's basically what I just talked about, the statistical methods of machine learning. And then we'll look at neural network applications of machine learning, and then get into more varied neural network algorithms rather than basic algorithms, which is what we will discuss that tonight when we get to neural networks. Then we'll do our project, which we'll talk about that probably a whole lecture, talk about what kind of projects we want to do, what are the expectations, and then you'll go off and do it, which I can't wait. Can't wait to see what everybody does on that end. I want some good industry applicable machine learning, which is not that hard. So we will be talking much more about that as we go. Okay, so everybody good? Everybody good to move forward? That was kind of a review, and just first slide also we talked about last night, but yeah, this is where it gets exciting. Breaking up the activities of a data scientist. We looked at the Venn diagram of a data scientist last week and broke it up into 3 areas, the engineering / computing, the mathematics and statistical. That's really the big part of mathematics that you use as a data scientist. And then, okay, what do you do with all this computer programming and statistics. And what do you do with it? That's where if you have the domain knowledge, you have somebody telling you, okay, this is the problem I want to solve, go do it. And it could be you yourself, it could be your boss. It's the business side of it. That's the domain knowledge. So okay, I had a question here. Does each one pick the project of their choice, or would you provide data sets to work with? Everybody will pick the project of their choice. But I'll have a list of possible projects, and there's lots of data sets out there. I know at my company we've got I got so many ideas on how to apply this in retail. And I mean, I'll think about whether we want to do like one of the Kaggle data sets, or just a miscellaneous data set that we get from a website of your choice, political data set or something like that. So sociological data sets, weather, stuff like that. There's many to choose from. So we will talk about that. Could be vision data set that you come up with, that you create. I think that would be cool. There's a lot of driving applications. Where you could go get your own data set. So we'll talk about that. All right. So now what we're going to do is kind of go through the main part. Oh, yeah, I didn't finish the slide. Okay, so within engineering, within computers, at the programming side, what kind of things do you do as a data scientist? We just talked about it, the data, pulling the data in. Kind of assumed here that you have the data, but that's also something that as a data scientist you will be going and doing is grabbing the data, getting it from somewhere. So I've got another question here. Yes, more real world data sets are where we want to go, definitely. Yes, Kaggle is great examples, but I would much rather have something more applied, more that pertain to your expertise, your area. Where if you're not working right now, what area do you want to go into? What's your passion? What's your interest? And if you don't know right off the bat where to get data in that area, talk to me and we'll figure that out. Got many resources for determining all of that. So okay, so what do you do with the data once you have it? You've got to do some data cleansing, which is some Python or R or SQL to get the data set for running your model against it, for doing your machine learning. There's some data that will not work, like if you're missing data, you need to fill it in somehow or neglect that data. So there's lots of processing that needs to happen. And we'll be spending a lot of time talking about that. Okay, other things you're going to do as a computer scientist or as a computer engineer, the pipeline development, you will definitely do a lot of that. That's basically taking it from beginning to end. That's your whole project, starting with the data, ending with a model that's trained and hopefully continuing to be trained with new data. That's the pipeline side. These couple of things in the middle, programming, creating libraries, creating algorithms, creating models from scratch. That's not something that most of us will be doing. If you're a data engineer, machine learning engineer, then you might be doing that, but that's pretty advanced. That's maybe it's open source and you contribute to it, and there's many examples of that. So you might be doing that. What we're going to do here, and why I have those asterisks, is we will be developing a couple of the algorithms from scratch, because I want you to understand these algorithms, how to program them. The basic ones, like neural networks, we will be doing that from scratch. Linear regression, we'll be doing that from scratch. K-means, those are very simple algorithms. There are a lot of bells and whistles you can add to them, but we will be developing the basics, in class. So don't worry, I'm not going to have you go off and do it yourself. We will do it in class, and then I'll have some kind of programming assignment for you to add maybe a bell and whistle to it. And the reason why, number one, it says few here, and number two, I will have you do it in the class, because it may be the only time you ever do it in your lifetime. If you're a data scientist and you're not deep into the models as far as the programming side, then you will just be grabbing these models as functions and plugging them in, plug and play. It's almost become commoditized these days. You don't almost, it's very sad, but you don't need to understand what's going on under the covers in order to do machine learning. And that's actually one of the reasons why I want to teach this class. Why I feel that need is because I want data scientists, the ones that as many as I can get to anyway, is I want them to understand these algorithms from a theoretical perspective, from a base perspective, from, okay, what's the math behind them? You don't necessarily need to understand it completely, but at least have been exposed to it, so that you can talk about it. That helps you very, very much understand the progression of these models, helps you understand and appreciate how amazing they are, how amazing machine learning in general is, where it's all going, where it came from. It's just, it's incredible. So that's probably the biggest thing I want you to get out of this class. And so we're gonna spend a good amount of time on all these different model algorithms. Okay. Another thing that a data scientist, or more like machine learning engineer, would be doing is work on speeding up algorithms. And we're actually going to talk about that more later, what that entails. But most people will not actually be doing that. They'll be more just using them. It's more like optimization, program optimization. So, okay. So that's generally what all the computer side of this is, computing side of it. We will definitely be going through it. So you will become pretty well versed in that side of it, if I have anything to do with it. Okay, so then the mathematics and statistics. So mathematics side, pure mathematics outside statistics, linear algebra is what you will need. You'll need to be able to read these papers. You'll be able to understand these equations, what they represent. These arrays, these matrices, tensors, vectors, scalars, and all the different types of numbers that go into these algorithms. It's just, you don't want to be lost when somebody presents this derivation, the understanding part of it. You need to understand some of matrix multiplication. That's probably the deepest that you'll need to go. We'll do some other definitions, but it's really not that big a deal. It's just gotta have it. Statistics, that's extremely important for understanding your data, understanding, the mean, standard deviation, how skewed your data is, how you can make it good and ready for a model. What kind of, data feature engineering, what kind of data manipulation you need to do. Evaluating your models, that requires some statistics. Telling which of your inputs, which parts of your data that you're training this on are important. That you may need to speed up your model, and not necessarily with the algorithm, but with what you're feeding it. So you want simplicity, so you may need to do some work in statistics, some feature engineering to get there. And there's statistics and mathematics that went into developing these machine learning algorithms and models, along with the programming. So a few of us will actually get that deep into it. In some of these algorithms, there are huge amount of mathematics, calculus. So, it's already done for us. So unless you're going to be developing new ones, we won't have to go that deep into mathematics. And then the domain knowledge part, which is the business sense, which is, okay, in retail, what kind of problems do we want to solve? How are we going to make our company more money? Because that's what happens in business. We need to figure out what the right prices are to sell at. We want to be able to predict what our sales are, so that we can make sure that these the stores are stocked. We want to have a good model for our distribution channels. Estimating how long something will get once we order, how long it will take to get to us. Those are all the problems in the business side that you will want to answer using machine learning. And also the visualization. Once you have something done, you have to be able to convince people that it works. And the visualization side is what will do that, because picture's worth 1,000 words. You want to give them graphs, meaningful graphs. There's many different types of graphs you can do. There's a whole world behind this. Kate Strachny. And some of us have perfected it. And some of us want to perfect it, want to, be able to show our answers, present them. So that's what the visualization part is. Plus, as we go through our, model development, we will need to see how things work, how things are looking as we go along. It's easy to tell whether something's correlated if you graph it. So very important. Okay, so that's all the stuff that you have to do as a data scientist. So I guess we're done. We can all say we're data scientists, because now we know what it is. Oh wait, we need to learn it. All right. So some interesting things. I don't know if I'm sure almost everybody knows who DJ Patel is. I don't know if he was a data scientist at LinkedIn, but he came out of LinkedIn and became a very famous data scientist, and ended up being our most important data scientist for the U.S. government. And he and one other person, forget his name, Hammermacher, I think I talked about it in my last lecture, coined the title data scientist back in 2008. Before that, you didn't have that. You had data analysts or engineers. data engineers. You didn't really have a lot of that either. It's when big data came along that then all of a sudden we needed that. But he made an observation that as a data scientist, you end up spending much of your time working with the data. And it says cleaning the data. I would say, I think what he's probably referring to also is this data exploration and feature engineering, which is helping your data along. It's making it useful in a machine learning problem. So, I'm assuming that's what he meant. Love to ask him. But yeah, it's preparation. It's everything before you actually apply the model. And then once you do apply the model, you may see that you need to do more feature engineering. Drop some columns, because when you create models, you can also see how correlated your data is through the model. And then if stuff's not correlated, if stuff is useless, you can drop it, then your algorithm will become more accurate. So, all right, so we talked a lot about this, but okay, so the engineering, I'm kind of breaking down these different areas in a kind of a different slice, I guess. The model and algorithm building. Okay, that's one part of your job as a data scientist. Some parts more or less than others. Like for instance, first part, the algorithm development. That's not something everybody's going to be doing, but some will be, at least, and will be all contributing to it, if not directly, indirectly, by using and talking about these different algorithms. So how did these algorithms develop? How did they come about from scratch? The first thing was, okay, we had a problem. Somebody said, okay, I want to predict this. We didn't just develop these algorithms without there being a problem already. Or like a big example would be new number, numerical recognition. You present it with a picture of a number, and okay, what number is that? That's a problem. So then some people sat around and said, okay, how are we going to solve this? And they talked about the approach of creating the algorithm. How do we want to do this? And I guess the next part, are we going to build on a simpler algorithm? Like for instance, go from tree, simple tree algorithm to boosted tree. That's where you're taking a very simple algorithm and making it more complicated. Or are we going to take an existing algorithm and add to it? That's another way an algorithm is developed. Another hyperparameter, perhaps, another feature that requires a hyperparameter, I should say. And hyperparameter is a tuning method. Like for instance, and we'll get to this with neural networks, is how many neurons. That would be a hyperparameter. That wouldn't necessarily be an extra feature. Maybe a hidden layer, add a hidden layer. That's a new feature to neural networks. Let me think, what else? All right, so that's how algorithms develop. Okay, so all right, another part of algorithm building is this abstraction process, which this is probably one of the things I like the least. However, it's life, so I have to get on with it. And it's hiding away the underpinnings of a process, a model, an algorithm. You know, that's you know, you don't, in other words, you don't have to recreate that algorithm every single time from scratch with the mathematics. You can just plug in a function as a black box, and that's great. And one of the things that's a big advantage of that is whoever created that abstraction, whoever did the mathematics, did the programming, you know, did it perhaps very efficiently. And it will always get better. You know, somebody's always going to be working on it, making it better. So it will become faster, more useful. So if you, and you don't have to worry about that. But over time, you know, you can get numb to how it works, you know, how it works underneath. So, which, you know, you lose some information, you know, some usefulness of these algorithms when you do that. So some of the abstractions that are out there, scikit-learn, you know, you have many model algorithms, models/algorithms there for you to use. Many functions, it's all built. TensorFlow is one of the most recent, and it's very excited. A lot of people love it. It makes creating neural networks, you know, it makes all this matrix mathematics, it makes it all very easy to use and fast. And you're able to offload this stuff off of your processor, perhaps, through APIs. Use AWS or Google, because you're just saying, I need a neural network. I need another layer added. This is how I want it to look. Keras is even a higher abstraction. You're not even involved with the math. It's super simple. We will go through all of these as we go further, as we get further in a couple weeks, because that's where on a day-to-day basis, that's how you're going to be applying your models, is through these different abstractions. And as you can see, there are more than just those three. Those are the ones that I would say, I don't know if they're the most popular, but they are definitely becoming popular. As you can see, TensorFlow is new and it just took off. This is all just as of 2016. Keras is newer than that, newer than this graph. Sorry about that. I should find another graph to replace that. But you know, scikit-learn's been around for a while, and other ones are coming up there. But it's like they're all, I won't say they're the same thing, but they all have the same idea in mind, to give you a tool set of machine learning algorithms to pull from. So other things you do as a, you know, on the computer, you know, is make what are you running it on? What hardware are you using? Are you running it on your machine? Are you running it on, do you have a GPU where you're able to take advantage of speed up in processing, the faster processor? Because we will get into this when we get to the mathematics. Actually, today we should be able to get into that in the time. Is, okay, what are the calculations that are going on? There are just a few calculations that are just happening over and over and over and over and over again, you know, gazillions at a time. So if you can have a very fast processor to run that, you know, not a very complicated processor, but one that's just specializing in multiplication, then that's extremely advantageous. So you have a new thing coming out where you're be able to take advantage of that. And we will look at that. It's fascinating on how that works. How you set up the parallel processing to do some of the work. Are you running it on AWS? This is something. It's just, are you running it on your machine, or are you running on a cloud machine? AWS or the Google AI Cloud. It's just the way to do it. I mean, for any size of problem, your machine's pretty limited unless you've spent a nice penny on it. So might as well take advantage of somebody else's machine for pennies. A few dollars, I guess. Okay, something else you do for the building in the engineering, and you're also using mathematics, is making your algorithm faster. Not necessarily from running it on a faster machine, but seeing where your memory can be used more efficiently, perhaps, or use less instructions. So that's something else you can do. With not much of us will be doing that. Okay. All right. So talking about these algorithms, as you can see, this is a pretty good picture of the different types of algorithms and applications of those algorithms. And I say types of algorithms because this is not actually the algorithms themselves. This is just a breakdown of okay, what are the different types of machine learning algorithms out there? And many of you are already familiar with this, and some of you just have never seen this before. So just want to run through it real quick. So you have really three different types. You have supervised, unsupervised, and reinforcement. It's actually a semi-supervised as well in there. And that's actually reinforcement, I guess, would come under that, where it's a combination of those two, supervised and unsupervised. So let's start with supervised learning. Supervised learning is where I have a data set, and I have a goal that I want my machine learning to do. I have something I want it to learn. I have a definite set of outputs, I have a definite set of inputs, and I want it to learn that relationship. So basically it iterates through a process to get to that point where it understands how to manipulate your inputs to be an exact output. And there are two types of outputs that we could have it learn. One would be classification, which very simply would be, is it a tree or not? Is it a cat or not? Or taking it further, is it a cat or a dog or a bird? Those are all definitive answers to a question, yes or no. Cat or dog, it's 1 or 0 is your output. Another type of supervised learning is when your output is not something like a class of items, objects. It's a regression, which is a analog output. Analog one, a number between 0 and 1,000,000. Let's say like a price. Having it learn what's the optimal price to sell at. Let me think what else. A count of units that I'm going to sell, something like that. It's not is it this or that, it's how many, how much. That would be a regression technique, but you're still setting your output to something and having your process learn it. And there's a subtle difference between the algorithms that you use, but many algorithms apply to both. And then you can see there's different different examples of each one of those types of learning. Okay, so another type of learning, so like say you don't have a definite defined problem to solve, definite output to learn. I just want my network to just classify things, but not necessarily, I don't necessarily know how it's going to come out with an answer. It's just going to divide up my learning data, my input training data into different classifications. It's going to just naturally see how to do that. And we'll talk about this much more. And it's basically that's clustering. It's just like, let's say I have a bunch of customer sales data, and what they purchased, and I want my algorithm to just break all the customers up into 4, give it a number, different groups, and then see what happens. And that's it's fascinating what kind of information it'll come up with. It may come up with seasonal versus everyday customers. It'll come up with something. Basically that's the customer segmentation problem. And also there's this dimensionality reduction, which, say we have 10 inputs to our neural network, then that's too many, it's taking too long. And we know that some of those inputs are related to each other. So if one's high, the other one's always high. Like for instance, if we're working at a similar margin, the cost and retail of a sale would be related to each other. So if we apply this dimensionality reduction to that data set, it'll combine those 2 inputs, which are dimensions of our data, together, and then we have a simpler model, simpler data set to feed our model, and therefore a simpler model, more accurate, perhaps. So those are some applications of this unsupervised, where we don't really know where we want to go with this data. We just want the network to simplify it, to come up with groupings. And then there's this reinforcement learning, which I'm so into this right now. It's incredible. It's game theory is part of it. Game AI is right there. It's basically taking a robot and saying, go learn how to walk, and just reward it when it moves its foot forward. When it starts to do something like walking, then you have an automatic reward system that's giving it. So it just tries different things and just throws away the things that didn't get a reward and keeps things that do have a reward. It's incredible. This is, I think, going to end up being, the be all and end all of AI, because it can encompass all the other areas. You can apply neural networks to this, so it can learn very, very, very complex things. So it's incredible. Anyway, can't say too much about it. All right, so that was all one part of the computing part of this, which is your model. Your model, and here are all the different kinds of models. Okay, another part of the computing is your model selection. So once you have your data, what kind of model do you use? Because we have a plethora, and we need to choose one. Well, the answer is you don't really choose one. You start with a simple one, and then get an answer, and then you want to improve on that. So generally, you have like a flow diagram, and you start, and it all starts with, okay, we've got a problem, and we have to get the data ready, for that model. So you have to work through that part of it. So once you've got to that point where you're ready, okay, now I have my data where I think it's could be, useful. Then you start applying models, and you start with the simplest one, which like a linear regression, just so you can test out, is there any meaning in this data? Your data may not be, and most likely is not, a linear problem, which we'll go much more into that later. It may be more complicated than that, but you'll be able to get some kind of accuracy, some kind of number, numerical accuracy out of it. So then you move up to the next level. You might try, just a basic tree, and then try the more complicated trees. And it's an iterative process, and it's just how you it's just how you do it. It all just kind of makes sense once you kind of get going. And I kind of picked a pretty complicated graph over here, but it's kind of get the idea of you work through a process. Is it more or less accurate? You go toward a more complicated model. They'll run slower. It's kind of why you want to start with something simple, because that'll run very fast. So you might get to a certain point and realize, okay, I need to really look at what features, what are my inputs, and work that down a little bit to get more accurate. And then then something you can do is some tuning, hyperparameter tuning on a model. One of the more complicated models, the one that you got the best results from, and see if you can get better. And at the end, okay, or any point in here, you have to stop, stand back. This comes from defining the problem. Am I good enough? Am I good where I've got to? And if the answer is yes, then you stop. You're done. You might still keep playing with it, but if you're not there, if it's still not accurate enough, you're still too far off from what reality is, that's what you're testing. Then you go back and keep adding, keep going with your models, keep getting more complicated models. And if you're doing a Kaggle competition, then you just see how far you up on the leaderboard. If you're at the top, then you might take a rest, get some sleep. If you're not there, then you just keep going, have some more coffee. There's almost no limit to how far you can go with that, because somebody else is always going to be pushing you. And it's done when the competition's over. So anyway, so that's generally the flow of doing machine learning. And here's another picture of that. Get the data. I mean, you guys can see this over and over and over and over again, and it's just going to become your life. This pipeline. Get the data, clean, prepare it, train your model, train and test, then improve. Go back to number 3, and keep going. And then maybe back to number 2 if you know more, if you can do a little more research, put it in front of other people, to get even more improvement on your this part, the preparation of your data. And that's the EDA. That's a very big part, which we will go into that. So next part, machine learning applications, which we have Actually, I'm going to do this a little bit backwards. I'm not going to talk about the machine learning applications just yet. Very excited about that, but I really want to get into the neural networks. What I'll do is I'll go through the neural networks first and then come back to this. So I've got a couple of nice, I love these slides. Ways that neural network can be applied. Mathematics, the world, sociology, soccer, automated soccer, robots playing soccer. You can paint. There's just so many things you can do with machine learning. And there's another. I couldn't help myself. Had to throw these in here. Okay, so let's just jump through these. I promise I will come back. Okay, so neural networks. These, back in, I don't know when, before the 60s, they started to understand what neural networks did in our head, in our brain, through biology. And this is a basic picture of what one neuron looks like, along with some other, some very interesting parts. So the neuron is here, the cell body, and it has some things feeding in and also shooting out. Coming into it are dendrites, which are, basically information flows through these wires into the cell body. When I say information, I mean chemicals and potential, electrical potentials, much like a wire, but much slower. You have electrons moving, just not at the speed of light, which is what would be electrons going through a wire. Much slower, but that you have 100 billion of them, of these neurons in your brain, so they're all working in parallel. So therefore, even if it's slow, the fact that it's in parallel means it's fast, because you have them all working at once, or many of them. So yeah, once we mimic this on the computer and we're running it, now we're running at the speed of light, electricity moving at the speed of light, it's going to go a lot faster. So robots are going to be much faster than us, be able to think much more quickly. Just we have to figure out exactly how they work and then teach them. And keep control, but that's another story. Okay, so from a neuron biological sense, okay, we have dendrites coming in to our cell body, and then the output of our neuron cell is an axon, which goes to the next neuron, and that's what is coming in here. All these little white arrows are axons from other neurons coming into actually this little piece, which that's a synapse. That is the connection that the neuron they're not showing here is affecting the next one. It has to pass through that synapse, and we'll get to that in a second. So it isn't just a direct connect wire from that one to the next one. Otherwise, all of these neurons would affect the next neuron in the same amount. We want to have all of them affect the next neuron in a different amount. So it depends on the strength of these synapses and the strength of these axons to how much the last neuron will affect the next neuron. So just basically it goes from axon to a synapse, then the information flows to the dendrite and then into the cell body, and then out the axon, and the process starts over again. Very exciting. This is the part I love. Okay. So here's another picture of these neurons, a little better picture. You have, again, these axons, hitting the synapse, hitting the dendrites of a neuron, all these, and then you have your nucleus, which here before we said the cell body, so it's part of the neuron. And then coming out the axon as an electrical signal. And then that is breaking out, these axon tips, going into the dendrites of the next one, and so forth and so on. Now, these other axon tips are going into other neurons. So we're not showing all the neurons here, but basically this neuron is connected to several neurons on the output. And these little beans here, that's called the myelin sheath, which grows or breaks down over time. And that all depends on several things. And the strength of that and the strength of those synapses is memory. Okay, that's what is recorded when we memorize something. It isn't the growth of new neurons. It isn't death of neurons is loss of memory, but it is these lines here, the axon, and how strong this myelin sheath is. So that is what the memory, where the memory is, and that grows and goes down over time. Now, we'll talk about the synapse next, the next one. Okay, so a synapse. This is where a lot of the magic happens. And you have the chemicals coming through here from the axon, passing through, moving through this area to the dendrite, to the next neuron. And this is where you need chemicals running around in here. You need lots of in the brain fluid. You have the different chemicals, and neurotransmitters is what they're called. They're all filled in here, and these things, as the electrons come along and stimulate this, they go to the opening and dump out their chemicals into this opening, and then that stimulates the dendrite. So if you don't have the right chemicals running through your brain, then this will not work well. These synapses will not work well. So that's kind of like the behavioral part of neurons, which is like depression or getting excited. Those neurotransmitters, depending on what's there, you could be sending a lot of information or not so much. Memory isn't necessarily here, but you could see how this is very important for the strength, and also the more synapses you have connecting the neurons, the better. The more information, and that grows with memory. Okay, so that's the structure of the neurons. Got a question? Okay, why are we learning about the structure of a neuron? I love that. Because it's my class and I'm teaching. No. This is, I feel that it is extremely important part of understanding a neural network, understanding where it came from. Why is this, why do we have this model, and where did the model come from that we're using? That's my take on it. By the way, you only sent that to the panelists. You didn't send that to everybody. But I won't say who asked the question. But it's just, to me, it's extremely important. And I'm just getting, have one more. I think this is the last slide. Yeah, this is the last slide on how a neuron works, how the network works from a biological standpoint. Then we'll get into the mathematics. We'll get to the parallelism how, how did we copy this in math and then in computers. So, okay, so so the information that flows along the axon is not just a number like a voltage over amps. Okay, it's actually a excitation. It's a wave. You have a pulsing. So the more excited you are, or the more that neuron is stimulated, the faster it's pulsing. So you have a slower pulse here coming out. You have a faster pulse here with C. D, you have, oh, I'm sorry, B. A, you have a slower pulse. B, you have a faster pulse. C, you have pulsing action. Like you have a pulse, then it's off, then it's pulsing, then it's off. Okay, so you can think of these as like this would B would be a 1, A would be a 0, C would be 1 0 1 0. Okay, and then D would be 1 and then 0, flat after that. So over time, the neurons are changing how excited they are. And it all depends on the neurons coming into them to how excited they get. And each neuron is going to affect the next neuron in a different way depending on that myelin sheath or the synapse. So that's that's physically how it happens, and then we're going to program that. Now this video, I'm not going to show it here, but it's amazing. I would strongly suggest watching it. A little bit mesmerizing. But it's back in the 60s. They were looking at actually hooking neurons up to in the visual cortex to sound and listening to how they were excited based on different activations. And different activations, there were different types of activations would do different things. So if you want to see that, like for instance, if this bright light was just over those X's, it would be excited, all of the X's. If it was the other way and not hitting, all the X's, then it would be very quiet. So this would be like an edge detection. So it's definitely worth looking at. When we get into convolutional neural networks, we're mimicking that very, very closely. I might come back to this and show a parallelization to how it actually works in the brain. Okay, so so I talked about how the information flows between the neurons. Okay, but how does this neuron, when does it send out a signal? When it gets excited. So how much excitement before it sends out a signal? Well, there's different ways that we've modeled that. And we'll actually use some of these, a couple of these. It's either on or off, right? The output is either excited or not. So that would be this binary step, where if the input is less than a certain amount, I'm not excited, I'm not sending out something. If the input is excited, then I am full on. Now, that isn't that useful in some cases because I can't take the derivative of this, and I'm going to need that, and we will see that later on. So we took a next step, and this isn't really a very good picture of a sigmoid, but a logistic soft step. But here, we basically just took this and flattened it some, where if we're not activated, if there's nothing coming in, then we're off. If there's something coming in after a certain point, it becomes on. And it's much cleaner. We'll see this again in a little bit. But here's a formula for it. And we have a smooth derivative for this, so we can, and basically the derivative is part of learning. We want to know what the the relationship to how much we need to change the inputs in order to get the output to be right, which would be a derivative. Okay, so there are several other functions that are used on your neuron, your cell body. Here's another one where it's actually a -1 or 1. It's very similar. Another, the arctangent. And then this one is off. It's off if it's negative. And then as your excitation, as your neuron gets more excited with coming from the previous neurons, it starts to take off as far as how much how excited it gets in sending out that pattern. And there's some problems with this necessarily being 0 because it's not doing anything if you have a negative. So therefore, we said, well, we're going to do a little bit negative. Just a little bit if it's if we're negative, if the input is off. Can I hold on a second here? I'm trying to. Okay, I just have to work around it. And then there's we're going to make it smoother. So we're going to approximate it with this exponential linear unit. Okay, and I have a little problem with the bottom of my screen, but it's okay. Okay, so all right, so that's how the neuron works. Hold on, got a question perhaps. Okay, the question is, are there particular situations where only some of the activation functions can be used? Trying to understand the application of each activation function. Okay, good question. There are different properties of each of these activation functions as far as like that derivative part, which we will get into that later. And that limits the usage of that, how well that neural network can learn if that's what we're using. Another limitation or advantage, I should say, of some of them over others is simplicity. How simple is it to calculate that activation function? Because we got to write code for that. And maybe writing the code is easy, but the computer has to process that code. It has to do that exponential if that's what the function is. And exponentials or tangents, aren't exactly that fun for a processor. So that's a big advantage of this, the ReLU, where it's a very linear function, whether it's negative or positive. Or it's nonlinear, but it's separate. Different parts of it are linear. So that one can be calculated very, very quickly, and I'm pretty sure that's why they're with this convolutional neural networks, which are huge. Why those use the ReLU most often. So those are the big reasons, and different parts of our neural network will use different functions, which we will get into that. Okay, so all right, so this kind of ties together everything we've talked about. Again, I've got the neurons showing over here with the axon, and this is a mathematical representation of everything we just talked about in terms of the neuron, which is why I went into the details. What we have is your initial inputs, or it's the output of a previous neuron, and we're going to call that X. It's a number in our case, so it's just a strength. It's a measure of something. Okay, in our neuron and our neuron activation back here, it would be the frequency, perhaps. In the way we're going to think of it is just a number between whatever, -1 and 1, perhaps. Depends on where it's coming from. It may be a price. It may be just a level of 0 or 1. Like if part of our information that we're using to learn is whether it has a garage or not. If we're talking about housing prices, it could be several levels. It could be like 1, 2, 3, 4, 5, 6, 7, 8. Like how many bedrooms? Probably be like 1, 2, or 3 mostly. So it's some number coming in, and then we have some kind of strength in between our neurons, and that's what this W is. So the axon, how much myelin there is on the axon, the strength of the synapse, the number of synapses between them. That's all represented in this W, which is multiply. We'll take that and multiply that by that X before we send it on. So it's a way of modulating the input through the dendrite into the cell body. And it's the same here. The X0 will be multiplied by the W0, the W1 will be multiplied by the X1, so forth and so on, for all the different inputs. So we'll have a set of weights for each connection between the neurons. Here we've got 3 inputs, so we have 3 W's. And the 3 inputs are the 3 X's, X0, 1, and 2. So to get how much this cell is being excited, we add those weighted sums together, right? Weighted values together, weighted inputs. And we come up with a weighted sum here. So that's this sigma. It's the add together Wi, Xi, I through 0 to 2. A little bit of math. So this is where some math comes in. And this is like matrix or vector multiplication, not necessarily matrix multiplication, but we will see where this becomes a matrix. And then there's just B, okay, which if all of these inputs are 0, then do we want our cell to be input to be 0? Not necessarily. We want it to have some kind of excitation. So we throw in this bias, this B, which in this case is not showing that it's having a weight. It's just flat, putting a number in there. And this is one of the hardest things to grasp, but it just becomes part of your language, is this bias factor coming in. And usually it is also modulated with another weight. And we'll see different forms of this with different formulas for this neural network input, a weighted sum. So once we have the weighted sum, we pass it through a function, which is one of these, activation function. So basically, if we have no input, no excitation, then we will generally have, we're along this side, we'll have low or 0 output, through this function. If we have a lot of inputs, if we have a lot of excitation, if all these neurons are wildly exciting our cell, then our function is going to take that and will be on this side. Now, if you notice, most of these, not these down here, but most of these limit on the positive side. They level out so that our neuron doesn't get too excited. It doesn't blow up. which is sometimes a problem with neural networks. Okay, I got a question. Why are W and X multiplied? W and X are multiplied because it's a modulating effect. Like if you have a strong connection between your neurons, then you're just going to kind of pass it through, or maybe even strengthen the output of the last neuron. If you so you have a big W. If you don't have a strong input, strong connection between your neurons, if W is like 0, then that's as if this neuron is not affected by the neuron coming in. That's extremely important concept. It's the way that we're affecting this neuron from the ones before it. The X gets multiplied by the W. And those W's can change over time. That's the, quote, learning. So, like for instance, let's say it turns out that your output really isn't much of a factor of X0, but it is a factor of X1 and 2. Like for instance, the price of the house is your output. The price of the house is high if you have 4 bedrooms versus 3 versus 2. Maybe that's X1 is how many bedrooms. Maybe the price of the house is not affected by, let's say, how many people live in it. Okay, there's not much of a correlation there. Could be no people live in it. Could be 10 people live in it. It might have a negative correlation, but that's still a correlation. That's still a function of it. W could be negative, where the lower X is, the higher it's excited. But generally, you're not going to find much correlation to how many people currently live in the house. So therefore, if you want your output to resemble the input, your input's passing through this function, you want that W0 to be very low or 0. Therefore, cutting off that axon, that other neuron coming in. So I hope that helps. What is the effect of the bias from each axon as the output of the whole neural network when Wi and Xi have proper values? Basically, what will happen is it depends on whether the bias is modulated or not. If it's not, in this case, your W's will just be lower to take into that effect of that B, so that the weighted sum is a little bit lower. That's what will be the effect of having the bias in there. Okay. So it's live. That's generally the effect. Okay, so here we showed 1 neuron, 3 inputs. Okay, here's another picture of the same thing, but with an unlimited number of neurons. Another question, perhaps. Each neuron is a logistic regression, correct? Depending on the function, yes. Depending on the activation function, yes. So yes, we will talk more about that. There's parallels of neural networks to the logistic regression function. Very, very simple logistic regression function. But we haven't gotten to that yet. Okay, so here we're generalizing. Instead of just 3 inputs, we have M inputs, and then a bias coming in. And see here it's different. They multiply the bias by a W0. They have all these weights that are those synapses. that's modulating that input coming into this sum, multiplying by. Sorry, I have electrical engineering background, so I think of modulating as multiplying. Oh, what are we up to? 28. Oh, okay, we'll make it a little bit over tonight. Hope that's okay. All right, so we're going to sum them all together, multiplying them, and then pass it through our activation function to get our output. So this is just another picture of a one-layer, one-neuron neural network. So now I'm going to get more complicated. Here's another picture of that same network, input layer feeding into a neuron. Now this, we'll show this more when we get into the derivation, but this is a linear regression. Each one of these is multiplied by a number, so it's all linear related. Your output's linear related to the input. This makes it nonlinear, this activation function, but generally it's linear. You can only do so many functions that way. If you want to do a nonlinear function, you insert another layer of neurons in the middle. Instead of just having one layer, now you have one neuron, now you have 4 neurons. You added one in here. And again, you have the same effect. You have W's on all of these. Feeding this, now this, instead of just going straight to the output, you feed these other neurons, which have exactly the same function that we had before. Same, it's got a summation and then activation function. And then the outputs of those act just like the inputs acted in our first neural network. And they feed your final output. So we're able to do a much more complicated function with this network. Sorry. So here we've got one hidden layer in our neural network. And this is kind of where the status of technology was back when I was in neural networks in the 90s. You didn't do much more than this. So, however, you can make it much bigger, add more neurons in the middle, more inputs. We only had 4 in the last one. Here we made 784. And then 16 in the hidden layer, and then 9 or 10 on the output. Okay, can activation function be different for each neuron in the network? Yes, but nobody does that. You do it sometimes for different layers, different types of layers, but you don't do it for each neuron. Just for simplicity. And there isn't really a reason to do that. Really, you want your neural network to be as generic as possible. So here the problem, and we're going to do this problem. This will be one of the first things we do. The problem we're solving here is this. It's an image recognition, the MNIST data set, which is a bunch of numbers, 10 numbers, handwritten numbers. You can get very, very good results in recognizing handwritten numbers with 784 inputs, and it's 28 by 28 pixels. The picture that's 28 by 28. Each pixel is representing an off or an on input, and then you can feed that into 16 hidden neural networks, hidden layers, and then have 10 neurons on the output. And those 10 neurons, each one of those is going to get lit up when you feed it a 0, 1, or whatever it is on the input. If it's a 1, it'll light up the 1. So a lot of arrows here. Specifically, there's 1 arrow for each connection. You have 784 here, you have 16 here. Therefore, you have 784 times 16 weights, arrows. And there's a weight there for each one of those. And here you got only 16 by 9 weights. So gives you an idea of how big this is. It isn't complex because everything is regular, everything's the same. It's just, lots of multiplication, lots of addition. So this is actually a pretty small one, but it's a great problem. We will do this and you'll be amazed at the results. Okay, so those were basic neural networks up until like 2005. Then things exploded. They started adding more hidden layers. And we're almost done, by the way. Here, if you do, instead of just one hidden layer, 2 hidden layers, you now have moved into the deep learning category. Before that, it's just not deep. You don't really call it shallow, but it's just not deep. More than one hidden layer, which means basically 3 layers. This is not really a layer. This is your inputs. Then you have a deep neural network, and different kinds of deep neural networks. This is a simple deep neural network, just one extra hidden layer. You have these other kinds like the convolutional neural network or recurrent neural network, autoencoders. We'll be going on to all of these in detail later on. Here's a very high level picture. This is what a LSTM looks like as far as the math goes. Extremely complicated. We will go into that. It's a recurrent neural network. One particular added thing to a recurrent neural network gives you this long short-term memory neural network. CNNs, convolutional neural networks, here's a picture of one which is fascinating. It's just, you can, great for visual, but also very useful in other, people are starting to apply them in many other ways. And this is all very recent that this stuff got very popular. It came about like around 2005. But I'm telling you whether this picture is car, truck, or van, or bicycle. And then here are all the different layers, different types of layers in here, which we'll go into all of that. Very, very fascinating stuff. So with that, talk about the homework for a minute. I've recopied the lecture 1 homework here. Get GitHub set up, post your GitHub on these, the sheet, the Google Sheet. Here's some help with getting it going. Very easy stuff. Get a LinkedIn going, get Python on your laptop. Here's how you do it. And then do some exercises in Python so that you get a basic understanding. Okay, so more homework. If you haven't seen lecture 1 or watched all of it, go ahead and get through that. You can click here. Once I show you this, once I pass this out, you can click on it to get there. Get on the Slack channel so that we can all communicate and share, and fill out your part of the that Google Sheet, so that we can all communicate and help us communicate. And that's going to be important for me to keep track of everybody. So with that, I think we're good. Appreciate everybody being on. Sorry, went a little over. I will go back and pick up some of that stuff earlier. Review some of this stuff. Go look more into neural networks. By the time we get to this next time, it'll be very helpful. I'm going to review some of it when we go into it later, but we'll be jumping in there. So appreciate everybody's attention, and we will talk next week. See you on Slack. All right. You're very welcome for activating your neutrons, even though they're neurons. They're neutrons too. We all have those, and they're all activated. I know it. Very welcome, guys. Just do the homework, and we're all going to do great stuff in here. Cheers. I'll stay on for like 5-10 minutes. If anybody has any additional questions. Appreciate it.